Hi, so in this video we continue the implementation of our binary search tree data structure. So let's get started. I'm going to create a class binary search. I'm going to call it BST object. It's going to have a init constructor and it's going to have a root node, and I'm going to initialize it with none. And we are going to have a method insert. It's going to get the data we want to insert in our binary search tree. And we have to check whether the if not self.root node, which means that the root node is none, which means that it is the first element, then we have to create a new node. So it's going to be like this. And else we know that it is not the first. Oh, we have to import. Okay, so from binary search tree ds dot node import node. I think it's going to work. Okay, so else we know that the root node is not none, which means that there is also a root node. So we just have to call this method, this self.rootNode.insert with the data, and we just call the method we have specified in the last video. So we decide whether it's greater or not, so we have to go to left or right and so on and so forth. So that's all about the insert method. The remove method is a bit trickier. We have a data to remove, and if the self root node, which means that it is not none, so we have elements, we have items in our binary search tree. We have to check whether the root node.data is equal to the data to remove, which means that the root is the item we want to get rid of, and we just have to temp node equals to node with none. I'm going to have a temp node dot left child is equal to the self dot root node self dot root node is equal. Oh, we have to, we have to call the remove method with data to remove, and the parent is going to be the temporary node. And else, of course, we have to call this remove method, remove with the data to remove, and none. So here we call the method we have specified in the last video, this one. Okay, we have 3 more methods. The get max, which is going to be, we just have to, if the self.root node, which means that it's not null, we just have to return self root node.getMax. Okay, def get min, it is basically the same. If self.root node, which means that it is not null. If it's none, it means that there is no elements. If there is no element, we cannot get the maximum or the minimum, so that's why we have to check it. we return the self.rootNode.getMin. Okay, and we have one more method, the traverse in order. We just have to return. I'm going to check whether, because if self.rootNode, if it's false, it means that there is no element, and if there's no element in a root, then there's no need to traverse it. Okay, so traverse in order. Okay, and I think that's all. Let's start. I think there will be some mistakes, but first of all, I'm going to import from binary search tree ds, binary search tree import bst. Okay, so I have a bst equals to bst. I will have a bst insert 12. I'm going to insert 10 -2 1, for example, and I want to traverse in order. So if I run this, oh, it's the previous. Okay, yeah, magically there is no mistakes. Anyways, if you are developing a software, there will be a lot of bugs, so I get used to dealing with these problems. But anyways, now it's in-order traversal. And in-order traversal, as far as integers are concerned, is the numerical order, and that's what we get: -2, 1, 10, 12. If you want to remove binary search tree that remove 10 and traverse in order, we should have missing 12. No, it's not. Remove 10 and traverse in order. It's not remove. I'm going to check it, and then we are going to move on. So here is the bug. The parent node equals the self right child. We have to set the left child, of course, to the equals to the temp node. That's why we were deciding in this. If it's not none, we initiate the temp node, the left child or the right child, and we have to assign it to the parent's left child. It's very important. And if we go back here, hopefully it's going to work. -2, 1, 10, 12. That's the in-order traversal. And then after getting rid of 10, that's going to be the numerical order, which is good. Now let's print out the maximum. Oh, I'm curious whether there will be another error or not. The maximum should be 12, I think. And yeah, it's working fine. Okay, I'm a bit relieved. Okay, get minimum is going to be -2, which is good. Okay, in the next chapter we are going to discuss why this approach is not sufficient when we keep inserting. For example, if we keep inserting numbers from a sorted array, that is binary search tree becoming very unbalanced. And if it's unbalanced, we end up with a linked list, and the logarithmic time complexity will be reduced to linear time complexity, which is much worse. So in the next video we are going to talk about the importance of balanced trees. Thanks for watching.